All right, so let's go ahead and get going. So really quick level set before I start telling you guys about FIDO. I like to give very interactive presentations. So it is actually incredibly helpful to me and also to everyone else who's your neighbor in the audience if you stop to ask questions as we go. Because the odds are if you have a question, somebody near you is also thinking it. And the closer to the slide that brought the question up that we answer it, the easier it is for everybody. Down? Awesome. Cool. So welcome to the FIDO intro talk. I'm going to sort of talk you through a little bit of how we got here, what FIDO is, and then I will probably start digging into way more than we have time for about what's going on in FIDO. So there's going to come a point in here where I'm going to have to ask you guys what you're interested in, because there is more than I can cover in 30 minutes. But if we can target things to what actually fascinate you, this will go really, really well. So, evolution of programmable networking. We're here at the Open Daylight Summit. You know, something very near and dear to me. I've been with Open Daylight since the very, very, very beginning. And there's been this huge focus when you talk about programmable networking, things like cloud, SDN, NFV, on the controller space, right? Building a controller to control things. But one of the things that we've learned over time is that you really, in order to meet your ambitions for the things that you want to do with your controller, you need to have a fully programmable, highly performant, highly scalable data plane where you can easily achieve the kinds of things you want at the right semantic level to express them. Right? Because you can wind up with things where you have to do a lot of work to do something semantically simple. That makes it hard to program. And you can wind up with things where you can't really express from your controller at all to a programmable data plane. And so we haven't really had that data plane, that programmable software data plane until now. Something that allows you to deliver dynamic data plane services. And that's really the problem that we're seeking to address in FDIO. So FDIO, FD stands for fast data. Typically FD.io will be pronounced as FIDO because we're cutesy like that. When you look at FDIO, it is fundamentally a multi-party, meaning there are many different people involved with a variety of different interests. Multi-project, meaning that there are many different projects within the FIDO community. Open source project, meaning that is a regime for open innovation, where anybody can come and work on what they think is a smart idea. Now, some of these other components, multi-party and multi-project, end up being critical for that last piece about being an open innovation regime. Because being multi-party means that we have multiple viewpoints on the problem. Being multi-project means that you don't have to go convince some inner cabal of people that your idea is a good idea. You can bring your idea as a project proposal to FIDO and say, I have this idea I want to work on. And the TSC will approve your project, the Technical Steering Committee, and you can go work on it even if there are people in the community who think your idea is stupid. Because I can't tell you how many times in open source I've seen people come up with what end up being brilliant, world-changing ideas that everybody thought were stupid the first time they heard them. So that's governance architecture-wise what allows you to actually be highly innovative in FIDO. As you'll see shortly, we also have the technical infrastructure that allows you, because of high degrees of modularity, to also innovate in a very free way. So most of the time when we're talking about FIDO, we will end up talking about networking, because we're basically all networking people here. But one of the things that we realized when we started bringing people together to form FIDO was that the future of I/O is converged. Networking and storage are not going to be things that you can effectively handle performantly separately in the future. Among other things, you start stomping each other across cache if you have your I/O for storage separate from your I/O for networking, and you thrash the performance out of each other. So this has to converge. The result of that has been that we came up with a scope for FDIO when we had our pre-launch meeting with over 100 people from over 25 organizations that looks like this in layers. So the bottom layer is I/O. For us, that's going to be network I/O. And so thinking in terms of network I/O, that's simply how do you get the packet from a NIC or a VNIC to a thread on a core really fucking fast. This turns out to be entirely harder to do than to say. And it's something, for example, that DPDK does really, really well. So that's the first layer. But you could imagine the analog for storage as well. The second layer is processing. We would think of that in terms of packet processing, which is how you do things like classify, transform, prioritize, forward, or terminate that data. For us, think routers, think switches, think network appliances that do things like load balancing and things like firewalls. Think WAN accelerators. Those are the kinds of things that we mean by the processing layer. And this is where the VPP technology, which I'll talk to you about shortly, really shines. Because architecturally, it has nailed how to do the processing layer in a way that is not only faster than hell, but trivial to extend with new features. And then the final layer is the management agent layer. So now that you have this freaking fast data plane, you'd kind of like to be able to control it, preferably from off the box. But it doesn't make any sense to stick the pieces that control it into the data plane. The data plane needs to focus on forwarding packets. So you want to have a data plane management agent that can control it. Further, by having a data plane management agent that is independent from the data plane, you can have different ones for different use cases. Because it turns out, and this is something we've learned over time as we've worked with a variety of SDN protocols, there is no one true protocol. Different northbound APIs make different problems easy and different problems hard. And so we have to have the flexibility to pick the right tool for the job. Any questions so far? Yes?
Can you go back to slide 3 for a minute?
Of course.
Talk about the right side of the slide.
Oh, things like creating a platform that enables things that are highly performant, modular, and extremely extensible. Those sorts of things?
Your real project goals. What are your success measures?
So it's interesting you should ask that. So because very clearly, the success measures of any open source project are that you have solved the problems you have set out to solve and that your work is being adopted. So the problems we're trying to solve are, in the most generic sense, as you saw from the previous slide on scope, are the problems of this I/O as it's converging and producing something that's highly scalable, highly performant, and modular enough that you can support a rich amount of innovation. I'll be talking a little, the reason I skimmed past some of those is I have better slides for that later. Does that answer your question about project goals?
That's a good start.
Do harass me later if I've not fully gotten to what you're wanting there.
Question.
Yes?
Do you have a comparison between FIDO and other similar products?
Later slides. Good question though. So, really quickly, FIDO membership, it's the ubiquitous logo slide. We have a nice mix between chip vendors, hardware accelerator vendors, network vendors, service providers, small startups. Basically, we all have this fundamental problem we're trying to solve, and we're trying to pull the entire thing together as a group. So I had mentioned earlier that FIDO is a multi-project consortium, right? We have multiple projects. So this just shows you some of where we stand with projects to date. So we have the core project of VPP, which gives us the underlying packet processing framework. Then we have a plugin project for NSH, SFC, that provides plugins to VPP, and I'll talk to you more about plugins shortly when we get to the architecture of VPP, that enable NSH header support. We've got O&E, the overlay network engine, which is basically a Lisp XTR, so it provides the Lisp XTR support. We have a sandbox. TLDK is a transport layer development kit. The goal there is to be able to have a fully user space host stack so that you can connect it to things like containers, you can connect it to things like even individual processes. Imagine a world where you could have each process carrying its own v6 address and the kinds of things you could do with network analytics there. When you move up to management layers, we have a project called Honeycomb. Honeycomb's very close to Open Daylight. It reuses many of the same components to expose a netconf yang and restconf API northbound. And then finally, for supporting purposes, we have sysIT, which does our large-scale testing, and I'll talk to you a little bit more about that shortly. And the downstream maintainers in the Ubuntu distribution for DPDK have started a project at FD.io to do their packaging work there. So, and we have a project proposal for the folks who are looking to maintain RPMs for downstream RPM distributions to do likewise. That has yet to be approved. It just came out this past week. So speaking really quickly about governance, I'm going to go through this really quickly because it's very similar to what you see in Open Daylight and most other sort of large multi-party, multi-project communities. You have projects. Each project has its own committers. The committers locally make the decision for the project. You have a technical steering committee, of which I am the chair. That technical steering committee's job is to try and foster collaboration between the projects and to handle approval of new projects. And then there's a board that handles matters of budgets and policy. So any questions from folks before I move on to VPP, and or am I going too fast? I'm going to take silence as golden there. So VPP is one of the projects in FIDO. It provides the core technology. It's known as the Vector Packet Processing Engine. And it lives here at the packet processing layer. So basically what it is, it's a user space process. It runs on Linux, although it could easily be ported to anything that has something that looks vaguely like a C library. We primarily use DPDK for the network I/O layer, although there are a few examples of things like AF packet that we do ourselves. It's been used on servers or embedded server systems, so it's shipped on product, both embedded and server-based, at volume. It's been under development since 2002, so it's a heavily battle-hardened code base. Effectively, it has the kinds of things that you build up over time when you've actually had to face the real world. For example, it has really deep tracing. So if you're trying to figure out why things are broken, you can turn on a trace for a limited number of packets, and you can actually sample what may be going on as things go graph node to graph node to graph node. Or the APIs that you address it with. You can record millions of API calls from your control plane. So you can play them back and figure out whether your control plane has a problem or your data plane has a problem. Lots of things of that nature exist.
Is this based on the DPDK mainline?
We'll get to that in just a second. So it depends on what you mean by that. So the VPP 1609 release uses DPDK for network, DPDK 1607 for network I/O. We don't use the DPDK packet processing features. Does that answer your question? Excellent. Yes? So the answer is sort of. And the reason I have to be very precise here is when we say vector packet processing, we mean something different than the vector instructions in the hardware. But in individual graph nodes, we actually do utilize those vector instructions in places to speed things up. So it's probably good to get into your question to talk a little bit about this slide. This ends up being the slide we talk about the most. This is the basic VPP architecture. So at its heart, VPP is a packet processing graph. You can see here, these are actually real graph nodes. They've been trimmed down a lot because there are about 150 of them in the actual VPP. And so what VPP does, the first bit of magic that it does around performance is, rather than taking the first packet and running it through the entire graph, and taking the second packet and running it through the entire graph, we take a vector of packets, as many packets as we can get from the network I/O layer, and we start by running them through the first node. Now, I will ask you to suspend disbelief for a moment about the splitting of vectors. I will talk about that, I swear to you. It's easier to understand in the first pass if you just presume that a vector doesn't split. So, we take this vector of packets, we run it through Ethernet input. Part of that decides which graph node it goes to next. And you traverse a path through the graph. By working on a vector of packets, you can amortize the fixed costs of processing those packets across the entire vector. So what are those fixed costs? Like the number one, yes?
So is the input, is it a multi-threaded, like let's say we process the vector, you still process in one packet at a time, you get all the packets. So is it multi-threaded?
So, yeah, so let me explain. So first of all, we do use RSS and those sorts of things in terms of bringing things in, and we do run multiple threads. But once you have a vector, that vector essentially gets processed in a single thread as you traverse those packets, because if you try and jump out to a different thread on a different core, you get thrashed and everything goes to hell, right? So in one of the senses that people mean, yes, it's multi-threaded, and the way that ends up being stupid and non-performant, it's not. So the first way, though, that this running a vector through a graph node gives you speedups, the first cost that you amortize is the iCache miss, right? So you load into the iCache the Ethernet input code, and you use that code across all those packets. And then there's a whole series of magical optimizations you can do inside that node because you have a vector. Things that involve memory prefetch. Because you're running through a vector of packets, you can prefetch the next set of packets. And you can prefetch lookups about packets. Things that involve predictive pipelining behaviors, where you can just assume that the world is a certain way at some stage early in your code, do a bit of work, check to see if you were right, and in the 1 in 1,000 times that you're wrong, you fix it, and most of the time you win. Also things like structuring your loop in such a way that you get multiple instructions per CPU cycle. So there's a lot of really cool magic that can happen inside the node, but what makes it all possible is the decision that you've made about processing a packet through a graph node, a vector of packets through a graph node. Now, let's say, for example, that you get a vector of packets that is heterogeneous. Into everyone's life, an ARP packet will fall, right? And when that vector comes in, that vector will get split, and that vector will take longer to process. It's an unavoidable thing. But there are two things about the statistics of this situation that are magic. The first one is that, typically speaking, usually, most vectors take a single path through the graph. And because they're taking a single path through the graph, effectively, you could almost think of it collapsing that path into something that is very, very friendly to the cache and executes very, very quickly. The second magical thing that happens is what happens when you lose. Let's say you get an unlucky vector. You get a vector with an ARP packet in it. So it takes a little longer for that vector to process. So the next vector is a little bit bigger because it's taken a little longer to get back to it. You process that larger vector through your graph. All those fixed costs that you're amortizing over the n number of packets, n goes up. The average cost of packet processing goes down. And so you will tend to catch up if you fall the tiniest bit behind. As a result of this, you get performance in terms of both latency and throughput from VPP that they're not deterministic, but they're reliable. And we'll talk a little bit more about performance here shortly. So here then we get to the next cool thing, which is the plugin architecture of VPP. So VPP has a plugin architecture where you can provide a plugin that can add nodes to the graph, rearrange graph nodes, provide new APIs, etc. So that I can go off in my own source code base, in my own separate project in Fido, as for example the NSH SFC guys have done. I can work on my code for the additional feature I would like to do. And that binary can be dropped into the plugin directory in VPP. And when I start VPP, it's there, it runs, it's part of the graph. This ends up being incredibly powerful because I don't have to work in the VPP source tree. I can work in my little source tree for my plugin. It means that I can work as a separate open source project within Fido if I want to, because I have a set of committers who are interested in, say, a maglev style load balancer. And they don't want to have to go through review from the people who are interested in the core, because the people interested in the core may be less interested in the work that they're doing. Perfectly natural. But they can do their work in their own space. It would also be the case that if you were a researcher, a commercial entity, someone who wanted to go off to one side and work on a plugin, you can go work on your plugin on one side without necessarily having to put it into the VPP code base or patch it. Yes?
Should the plugin be written in C or Lua or?
The plugin's going to have to be written in C. The level of black magic is really high. Other questions from other folks? I appreciate your questions. I want to make sure we catch stuff from other people. Cool. So this is the first magic thing, which is the modularity. And this ends up being amazing because you have an ecosystem where people can do innovative things in their separate projects, where people can do commercial things if they want to that act as plugins in VPP. Okay, 5 minutes. We may not get too deep into this, apologies guys, but we'll at least get through the architecture and a little bit of the performance. So the final thing, and I'll talk about this quickly, is what you can do here with hardware acceleration becomes truly magical. Right? We move from a world where hardware acceleration has to be about certain very defined things like float action tables, to a world where you can effectively think of substituting hardware for any collection of graph nodes in the system. So anything you think you can accelerate, you can do crypto faster. We had a presentation on this yesterday at the Fido Mini Summit. You can do any kind of acceleration thing you can think of write a plugin and have your plugin rewire the graph so that when your hardware is present, rather than going through software nodes for those, you go through hardware nodes. Essentially what you get is an output node from the point of view of VPP that hands off to your hardware, and then an input node that when things come back from your hardware re-injects into a point in the graph. So the level of innovation you can have for hardware acceleration becomes tremendous. I'm going to go really quickly through this. Feature summaries. Basically, VPP is a fully feature-rich vRouter, vSwitch, all the things you could imagine, thousands of VRFs. By the way, all these slides will be online shortly. This was the list at initial launch. Since then, we've had a large number of contributions from a very broad array of people, which resulted in the 1606 release in June, which brought in a whole bunch of new features, followed by the 1609 release that we had here just now in September. Again, more features, so very rapid feature acceleration. Apologies for going a little too fast. So performance, this is a comparison of performance that was done by ANTech last year between OVS DPDK and VPP. What you see here is that VPP maintains line rate for both L2 and L3 switching, even as you scale up to thousands of bridge table entries and millions of routes. The performance you see from OVS rapidly falls off. More recent benchmarks have been done with a box that has 1240 gig NICs. And in these more recent benchmarks, what we've seen is a throughput of basically 480 gigabytes per second, basically half a terabit per second, and 200 million packets per second with millions of routes on the routing table. In the case of V6, 2 million routes. And then in the case of V4, which you'll see on the next slide, 8 million routes with 2K whitelists. And we're able to maintain that throughput in spite of having large routing tables, large whitelist tables, et cetera, which is truly phenomenal. And what's even more phenomenal here, frankly, is we're not the bottleneck. The NICs are the bottleneck. If the NICs could give us more packets, we could process them. We spend most of our time working on very small vector sizes. We could take larger vectors from the NIC if we had to. It just can't give it to us. How are we doing on time? Okay, so real quick, because I've just said a hell of a lot really fast. Questions before we have to wrap up. I'm sorry I didn't get to everything. There was never going to be time in 30 minutes. Yes?
What's left to be done? What's the next steps?
So one of the lovely things about the networking industry is there is no end of creative solutions to the problems we created with the last creative solutions. So there's a bunch of stuff that people are interested in doing. I was just talking about somebody who was wanting to do MPLS over GRE and then NSH over MPLS over GRE. There are innovative things being done in terms of producing test networks with what we call our VPP Lite. We have people who are looking, as I said, at doing host stack work and doing integration with a bunch of things related to containers. There's some desire on the Honeycomb side of people to take the Open Daylight BGP stuff and put it into the Honeycomb data plane management agent so you can have a BGP agent sitting right down there right next to your data plane for doing things like segment routing all the way to the edge. What it really comes down to is we have finally gotten to the point where you can do everything that you have imagined as a network operator, a network protocol developer, a network software developer, all those places where people told you the ASICs can't do it. You can now build the data plane piece in FIDO, build the local data plane management agent in FIDO, build controller apps in ODL to control the whole thing, and actually really kick ass for the first time. You no longer have to hit that damn wall. Other questions? Yes?
You said it was started in 2002.
The-
What's new, what's old?
The code development was started in 2002. The open sourcing happened in February of 2016, this year. So basically, it was a run through, it's basically had that evolution and that hardening process since 2002, and it's been shipped in a variety of products, but it was open sourced in February of this year. Other questions before they throw me off stage? All right. Thank you all. You've been a marvelous audience. I appreciate all the questions. I'll be putting these slides up, which have a lot more than I got a chance to get through, up on, if you go to wiki.fd.io, we have a presentations page off of that you can find off the main page, which will have this deck and a ton of others. And I'm more than happy to talk to anybody who wants to talk about this in the hallway, or at any other point you can corral me in the rest of this week. Thank you. much.